So we're going to be talking about jogging. So most of you have already been jogging the robot. What does it mean to be jogging the robot? Hmm? Using manual control. Okay. So manually moving the robot with the teach pendant. We have coordinate systems in joint, world, tool, and user. And the max percentage of speed you can have is at 250 millimeters per second, or 10 inches per second. That's the fastest these will move in teach mode. Why? Because it gives us a chance to make sure our fingers and such are out of the way whenever that robot starts swinging around while we're programming it. So joint coordinates, each axis can be done individually, as you've seen. The robot utilizes, all right, and for those of you on the ABB, you know that you use a joystick to jog it. So are the plus and minus directions the same in all industrial robots? What they're talking about is if you go, well, let me go back this way. So a robot, whenever you're looking at the teach pendant, if you do plus, it's going to do one way. If you do minus, it turns the other way. So what they're asking here is, are all of them the same in how they're set up to do this? So the Fanic and the Motoman are set up to where joint 1, that's going to be your base, plus is to the right, negative is to the left. Huh? Yes, I'm recording it. You're good. So you have joint 1 that's plus is one way, minus is the other. And if you go here to the KUKA, it's the exact opposite. Not on all of them. Looks like it's just strictly on joint 3 and joint 1. Those end up switched. So joint 3 being your shoulder movement up and, your elbow movement in and out. Joint 1 being that rotation around the base. So really not that different. Then we have what's called 3D or Cartesian. It was not developed for robots. It was actually used for flight. Because when you fly anything, if you're doing a plane, a hang glider, parachute, what have you, you can move in an XYZ pattern. The aviation industry did it first. We actually adopted it for the robotics. Because robotics were not even thought of until the 1800s. Late 1800s, that. So they pulled that particular set off the aviation industry. All right. So world coordinates. The origin is at the center of the base. The teach pendant controls are used to joint jog axes 1, 2, and 3. And jog the robot X, Y, and Z relative to the center of the robot's base. The teach pendant controls used to jog 4, 5, and 6 jogs the tool center point in roll, pitch, and yaw. Okay. So essentially, Cartesian coordinates is all about where that base of that robot is and which way you're moving from there. Does that make sense? It's also called the right-hand rule of robotics. We're about to talk about that. So the right-hand rule for robotics is used to determine the direction of a Cartesian jog. All right, so you can do this with your fingers. Z is always up and down. X is in and out. Y is left to right. That's called the right-hand rule of robotics. Okay. And yes, that is a very hard and fast rule. Doesn't change. Everybody good? So are the X, Y, Z jogs directions all the same on industrial robots? The answer is yes. Why? Because the way the robots are all based, they all work from the same. It's why whenever you go to a different robot, it's really not that hard to figure out how to program it. Why? Because they work with the same instructions, they just do it in a different syntax. Does that make sense? Everybody knows what a syntax is, right? It's the programming language. So you have, for the simplified version of it, how many of you own Apple iPhone? How many of you own an Android? So if you've ever grabbed somebody's Android, if you own an Apple, it's a little bit different. It does the same things. It is a phone that makes phone calls, right? But the difference in the operating system takes you a couple of minutes to have to learn, right? It's the same for all the robots. Once you learn how to program one robot, it's a lot easier to go and program another. Why? Because you know what it's supposed to do. You know what it's supposed to be able to do. All it takes is figuring out what language it is speaking and learning how to make that language work for you. Does that make sense? So we have tool, roll, pitch, and yaw. So yaw is your wrist moving left to right. Roll is rotating your whole arm. And then pitch is your hand moving up and down. What we get to do with our arm and our wrist, it has to do with 3 joints. So is the roll, pitch, and yaw the same direction on all robots in the lab? And the answer to that should be yes. It might just be labeled something different. So if you look here, roll, pitch, and yaw for a Kuka, that's the guy down here, he labels his as A, B, and C, versus Fanuc and Motoman labels theirs Z, Y, and X. It still does the same function. It's still going to make the robot's wrist movements. So we have a tool center point. We've kind of talked about this before. What is a tool center point? Not so much where the tooling goes. What else could it be? Yes, it's where you're trying to actually perform the work. So if it's a welder, it's right at the tip of the welder. If it's something like a paint sprayer, like this picture right here, you don't want it to be sitting on top of the sprayers. You want it at a distance that's going to give you the best coverage, right? So tool center point, we generally are going to shift it from where it sits at the base of the robot arm right here before you connect the tool. Excuse me. Where you connect the tool. So what we have to do when we program it is we have to move that tool center point out to where we're actually doing the work. Makes it a lot easier to do that. Okay. So why would we want to do and change the tool center point is because we want to, when we're programming it, one of the best things you can do with a lot of robots these days is you can program them virtually. So if you go into the virtual world, it's much easier to program a robot that has the physical limits and is able to know where that specific tool center point should come down to. Okay. So when you're using the tool, I'm sorry. So when you're doing a tool jog, the whole thing you're doing about a tool jog is jogging it. Every part of the robot is moving around that tool center point. If you give that tool center point and tell the robot to keep it in this direct orientation and in this direct way, that's where it will stay while you are doing other operations. Does that make sense? So I'm not trying to read all this off to you. I'm trying to think of better ways to say it because it gets a little wordy. Are the jog directions for tool coordinates the same on all robots in the lab? Answer to that is no. Because your KUKA, your x-axis is off a little bit. So there are some differences as far as the tool jog. But again, that also just has to do with syntax and how you're working with that robot. Everybody's got their own way they're going to play, right? So we also have user coordinates. So what a user coordinates is mainly for is one of two things. Either you've got the robot in a different kind of position, like you mounted it to the wall, you mounted it to the ceiling, something. And it also can do with your workpiece. Because if your workpiece, you have to be very specific about something, you can set up user frames to work with what you have to work with. If that makes any sense. So what they're showing you here is that because this surface is tilted, it makes it a lot easier if I can go in and teach what is called a user frame to let the tool orient itself against that workspace. Okay. All right. And that's the end of that real quick, guys. All right. So short and sweet. Any questions on that? On how to jog the robot or anything? All right. So while we're at it, I'll go ahead and tell you what you kind of need to be looking out for on the test. You need to know the definition for what an industrial robot is. You need to know the placement of e-stops. You need to know what you have to consider for safety. You need to know why we jog robots, the different motions that you put in a program. You need to know the difference between a closed loop system and an open loop system. What does it mean to be control reliable as a circuit? Trying to see if there's anything really big in here that y'all might not remember to go over. If y'all remember when we went over the level 1, 2, and 3 safety systems, you need to go back over that. You need to know the difference between the orientation and position axes. And that's about it. There's some other stuff scattered in there, but I can't give you all the answers. All right. Everybody good? All right. So we will be doing the test on Monday, guys. Let me go ahead and stop this for